Okay, YouTube, in this video we're going to begin our module on using matrices really as tools in order to help us solve systems of linear equations. And so what I want to basically start with in this video is talk about what a matrix is and how we use it to organize information very efficiently, and then talk about also how we could use that representation to easily find solutions to a system of equations. So let's go ahead and start with this. When we talk about a matrix, like what a matrix is in math, consider this chart up here. It says the average weight by age, and so you can see the different age groups here and the difference between men and women, but you see this nice organized table here. And so this table, one thing we want to comment on is that it has two rows. Okay, it looks like, and we have 1, 2, 3, 4, 5, 6, 7. We could say that it has 7 columns, but we have this rectangular array, and anytime we organize numbers into a rectangular array that has a certain number of rows and a certain number of columns, and we surround the data by brackets like this, what we're doing is we're organizing it into what we call a data matrix, or at least a matrix. And so a matrix, to define that, as any rectangular array of numbers arranged in rows and columns and having brackets, is called a matrix. And so when we talk about a matrix in general, we'd say it's this matrix full of little individual entries in rows and columns. And so we're going to say rows go left to right, and then we'd say columns go top to bottom. And this is very important here, that we distinguish between the number of rows which go this way and the number of columns which go this way. Now also, these entries that you see inside of this data matrix up here, we just refer to those as the elements of the matrix. So the numbers inside the brackets, we call these the elements of the matrix. But basically, again, it's just a really efficient way to organize information. And so talking about that efficiency in organizing numbers in row and column format, basically we use these to display information, but also to solve systems of equations. And so we'd say that since systems having two equations and two variables are easy to solve by substitution and elimination, basically this entire video is going to be, or module is going to be focused on systems that have 3 or more variables involved with it. And so when we talk about a 2-variable system, something like, this here we'd say is 5, maybe, I don't know, I'm just kind of making this up, you guys, and we say this here, maybe minus y is a -1. Basically, we've seen systems where we have 2 equations and 2 variables, and we have methods for solving these that are really, really easy to use. For example, if we were to add these 2 equations together, we would get, 5x is equal to, a negative or a positive 4 here, because our y's cancel out. So really what we end up with is x is equal to 4/5. And with respect to finding y, what we've been doing, or what we would do, is plug it back into either of these first equations, because what we're looking for is an xy pair that would make both equations true. Now, I'm not interested in finding the value of y here, but basically this idea of solving a system here, we are going to be using that matrices to help us do this in an efficient manner. So we're going to start by introducing the concept of an augmented matrix. Now, an augmented matrix has a vertical bar separating the columns of the matrix into 2 groups. So we say that the 2 groups that we represent are the coefficients of each variable, and they're placed to the left of the vertical line, and then the constants are placed to the right, with respect to our system. So we say if any variable is missing, its coefficient is 0. So looking at these 2 systems here, what you're going to see on the left is just some system of linear equations, where in this first one we have 3 equations, equation 1, equation 2, equation 3, and 3 variables, x, y, and z. And so all organized thusly, we could say our constants on the right are our coefficients on the left. We could see that an augmented matrix, again, has to have brackets around it, but is really this bracketed row column organization, where what we have is our vertical bar, and this vertical bar separates this into 2 sections. So you'll notice on the left here, we have all of our coefficients of our variables on the left. So that is to say, if you had a system where, the 2z was on this side of the equation, you'd have to pop it back over onto this side before we can do anything. And also it is to say that all of our variables need to be lined up by type. So our x's all have to go in this first column, our y's all in the second column, and our z's all in the third column. But if that's the case, then really we're saying this is our x column, our y column, and our z column here. And these right here on the right are just the constants of the system. And so really what we're doing is we're eliminating the need to have to write equal signs every time, to have to write x's, y's, and z's every time, and just really working with the coefficients and the constants. Now, looking at this system down here, it's augmented matrix. What I want you to notice is that for any places that lacked a variable, like we had no x's or no x's and no y's down here, we would say that's the same thing as 0x plus y, 0x plus 0y plus z here. So if that's the case, what we're going to do is anytime you are missing a variable value, we have to fill in those entries inside of our data matrix, say in the second row, first column, or the third row, first column, and second column with zeros here. But you can see elsewise, we have our coefficients here, 1, 2, and -5, 1 and 3, and 1. and then over here we have our constants. And so looking at this particular arrangement here, this would be a really beneficial system because something organized in this way where we had nothing here, here, and here, we would already know the value of one of our variables, and therefore we could plug that back in, say for z here, and find y, and we could say y and z, we'll plug those back in up in the first equation, go find x, in a process we call back substitution. But for right now, all I want to worry about is, could we write a system in an augmented format here? So basically, that being said, let's go ahead and talk about our goal in solving a system of linear equations and kind of harken back to what I had mentioned here, that if it were in this form here, this form with zeros underneath here under our main diagonal, what we'll call it, then we would be able to see that easily we'd be able to find the value of our last variable. So that being said, it says our goal in solving a system of linear equations in 3 variables using matrices is to produce a matrix with ones down its main diagonal from upper left to lower right on the left side of the vertical bar. So to look at our diagram here, our goal is to get something that's in this form right here. And so we're going to give this a name here. We're going to call this row echelon form. Okay. And so row echelon form is this form where we have ones down what we're going to call our main diagonal here. So this is our main diagonal. I'm trying to write it diagonally. But our main diagonal here, and you can see that we have ones down that to the left of this vertical bar. Now also, we would say that zeros occur below the ones. So you'll notice that these are entries of 0 here. But if that's the case, again, what we would say is that our matrix would be in this form, this general form where one's down the main diagonal and zeros underneath it. But we'd also be able to say then, whatever this variable is right here, this x, y, or z, this is maybe a z right here, we could say z is equal to this constant f. So we say if a through f represent real numbers, then the third row of this matrix really gives us the value of one of our variables, kind of like over in this instance here, we already know that z is equal to 4 just because of this third equation, if it's in row echelon form. So we say that the other 2 variables can be found by using back substitution. And by back substitution, what we mean is if you already know the value of one of your variables, that is in our ordered triple here, x, y, z, if we're going to write our solutions this way here, then we would say we already know the z value is 4. Let's plug this back into the second equation to go find y. And then from there, we'll plug y and z both back into the first equation to find x. So this idea is that once we get it into this form, then we can just use back substitution to solve for the values of our variables. So here's what I want to do to finish off this video. First thing is, I want to try to write some of just our own augmented matrices here. So you see we have a couple of systems. Our first system here has 3 variables and 3 equations. And so if we're going to write this out, you know, naturally we'd have 3 rows, one for each equation here. And we'd say 1 is our coefficient in our top row here for our x. We'd say 1, 10, -2, and then we're going to put our vertical bar here. We'll put a 2 as our constant in that first row. Now for the rest of this matrix here, we have a 5, excuse me, a 5, a -3, a 4, and a 0. And then our last row, we have 2 x's, 1 y, no z's, so 0 z's, and 6 constants. And so this would be our augmented matrix here that has 3 rows, okay, 3 rows and 4 columns, 4 columns. So now looking at this next matrix, you notice that we have an x, y, and z, but we have 4 equations, and this will happen from time to time, but that's okay, we'll just make 4 rows. And so just like we would in this last one, we'll fill in our coefficients first, and then our vertical bar here. So we say 6, suppose I could fill in all of our constants here while we're at it. There are constants, and then our second row, we had a 1, and a 4 respectively for coefficients. We have a 2, a 5, and a 20, and then we have a -1, a 2, and an 8. And so here's our augmented matrix here. So for the last part of this video, what I want to do is, given an augmented matrix here, what I want to do is write the system that's associated with it and then solve for the variable values by using back substitution. So essentially what you could see here is that there may be a system associated with this, and if I were to put in variable values, I suppose I could use a, b, and c, but I'm inclined to use x, y, and z is what we see a lot of the time with systems, or at least linear systems. And then our constants on the right here, our system that would be associated with this thing that's in row echelon form having ones down the main diagonal and zeros underneath it would just be 1x minus 1y plus 2 z's, and this would be equal to 4. Now our second equation would just have been y minus 1z is equal to 2, and then our last equation would have just been that z is equal to -2. So the first thing I want to do is indicate that we already have this solution value here. And so we're going to say solutions. Now I want to write this two separate ways. One way I want to do it is as an ordered triple, an x, y, z triple. So we know that -2 is the value of z, but the other way we can write that also is just that z, people, is equal to -2. Now we want to go find z. Now this process of back substitution essentially is this process of now saying that since z is -2 in all of our equations, let's plug it back into one of these other equations here, most specifically the second equation, so that we can solve for the value of y. So what we get is this, we get y minus z is equal to 2. Therefore y minus this -2 value here, okay, is equal to 2. So therefore we have a plus a positive. If we were to subtract 2 from both sides now of this expression, this equation, we would get that y is equal to 0. So I'll put a box around this, but I also want to put this up on our ordered triple here. And so now that we know y is 0 and z is -2, what we're going to do is we're going to go place these two values back in our first equation that said x minus y plus 2z is equal to a positive 4. So now, not knowing x, but knowing y and knowing z, we say 2 times z, this is all 4. Let's plug in 0 for our y and -2 for our x. And what we're going to see here is that we get this x minus 0 minus 4 equals 4. In other words, we get x minus 4 is 4, and therefore x is equal to 8. So I'll put a box around this and we say that this is 8. So one thing I want to say about this here, and this is just our solution, this one ordered triple, but these are our solution values, is essentially that if you were to plug 8 in for x and 0 in for y and -2 in for z to all three of these equations, we'd say that this is a solution to the system because it satisfies all three equations. So satisfies all three equations. So as we go forward, what we're going to look at is essentially this idea that we want to take a matrix and we want to write it in this row echelon form, this ones down the main diagonal with zeros underneath it, so that we can easily solve the system that's associated with it. Cheers.